This podcast is brought to you by HEC Paris.
Thank you very much for having me here. I mean, it's really a pleasure, and I have to say, so I mean, Lauren and Veronica, even though it's a bit weird that as a thank you, in return I have to criticize the paper. So maybe after that I will buy some bunch of flowers or something. But you know, here we are. So that's my job today. So okay, so you can make a bit. Can you make it a bit larger? Oh yeah, sorry. Okay, so I mean, Veronica did a fantastic job in going through this rather dense paper. There are many things going on, and so I kind of summarize this. I mean, there's a different order, but what this paper does, so it's concerned with inference on asset pricing models with incomplete information. Okay, so a vast literature, and in particular, the first sort of contribution is to think about good ways of making inference of these models. So there is this keyword here that is popping up in the title is efficient methods, which of course kind of give us a lot of appetite as econometricians. On top of that, then looking at proposing a particle filter for the model in order to estimate the joint distribution of beliefs and fundamentals, which are the goal of the econometrician. Then propose a test of moment condition test, in particular like sort of twisting towards tests of rational expectations. And then there is a very nice empirical illustration of a Lucas tree model with a switching multifractal dynamics. So the starting point is this asymmetry, and where is the asymmetry is coming from? Can you make it a bit like zoom it? No, I think you can go. You go before Control, and then you do Control plus. Maybe. Yeah. So as I said, there are several actors. So nature, God, and which draws the state of nature, MT. Then there are agents that they want to make inference on M. And they have a lot of information. So they know the condition distribution of the signal given M. They have a pre-distribution of the transition density, if you want, the transition distribution of MT. And therefore, by Bayes' rule, so these are a rational agent, they work out the posterior distribution. And that's the goal. And then there is another actor, which is us, which who of course contains again, this is an issue which I'm going to discuss a bit, but they assume that it contains a small information set, and they observe only some information, and I sort of pin that down. Okay, so they collect information in RT, and RT basically, effectively, for example, in the application is say current and past returns, and then some idea of the distribution of the agents. And of course, the goal is to make inference on the joint distribution of MT and pi t using this distribution. And this is a fully parametric model. It's completely specified. So all is about making inference on this finite dimensional vector theta. So that's what they do. Of course, if pi was known, then Emily suppose could be computed. I mean, there is the issue of pi t, but they can play the same role as the traders, and otherwise, things get a bit messy. So this is a very, very interesting paper, and I think it's quite welcome to have a paper that looks at rather sophisticated models, but also try to sort of develop some inference methods and try to estimate these models as seriously and as sophisticated as they deserve. For example, I've seen in the past a lot of very interesting, challenging models which once compared with the data, they really sort of were judged by a bunch of regressions, which is not bad. The preliminary result is fine, but if you have a model which is very sophisticated, you want to use that the sophistication to make inference and to be perhaps more precise about whether a model is a good model or not. Okay, so here are some comments. Okay, so just for the sort of I'm using the distinction the 1, 2, 3, 4 type of points of contribution that made by the paper. So asymmetry. I mean, who is the econometrician? Sometimes, I mean, for example, if I think at the discussion that Peter Phillips gave this, early on, I mean, that instance, there was no difference. So the competition has all the information. The competition was working directly on the front line and could make some judgment about state or nature, in the case, the bubble. So here, I mean, I understand that from an economic point of view, it could be interesting, say, as an academic to understand, to have a judgment of what are the views of the market and so forth. But effectively, I mean, another characteristic could be someone who is reading the market. So, say, an econometrician who sits in a quant desk and wants to know exactly about, forecasting the future. And that's, that's a distinction that, I mean, nowadays perhaps is more and more, or less and less important nowadays. So, I mean, somehow I feel not so happy about this sort of stark distinction. And the other thing is about, talking about the models. The models, I mean, the paper is very ambitious because it starts very, very general, perhaps too general, and then in the application, consider a very specific parametric model. Now, if you read sort of casually, you might think that, this sort of Markov, low Markov law that is behind the scenes, of course, is paving the way for the multifractal model, which is a superb, very elegant structure, but is one of the many possibilities. So maybe I would be more convinced, for the sake of this paper, that it's not just about sort of proposing the multifractal as one possibility to explore other parameterization, so that we could really see, appreciate the sort of the proposed inference methods at a wider scale. Can you just scroll down? Maybe it's me. Okay. For example, other features. For example, these low order Markov features. I mean, I understand again for computational reason is important, but can we generalize, for example, to higher order Markov? And this goes back also to, for example, some features of the data that they used. Remember, for example, again, and this is something that I've been puzzled that the fact that you have a Markov structure doesn't mean that you have a nonlinear model and vice versa. So, for example, Markov chains, we know they have a bar representation mark the difference, and then you can cast this pretty easy with classical methods. So I think that would be should be perhaps clarified. And again, we know, for example, that I mean, one of the claims of the paper is that you have to advocate moving away from classical methods, family, and to use it, simulation-based because there is some problem of tractability. Now, I think again, I found it a bit confusing. So, is the problem computational? Is the problem of numerical solution? For example, we know that classical way of say think about the example of stochastic volatility model, or in general other classical model, low memory models. We know that the Kalman filter can even handle a rather large, even a possibly infinite dimensional state variable. So the fact that the latent variables, the space of the latent variable is augmented, is probably not per se a sufficient condition to look to necessarily buy this technique. It might well be, but I have really to be convinced. And I suppose it depends on the setup. Now, efficiency. Now, for example, the proposed technique is basically using this objective function, which is which considers the sort of perfect information likelihood function. Remember, it's a perfectly specified model, and it's setting up this sort of measured distance, so that then you take the first day condition and you use this as a moment condition to build your estimator. But I mean, I'm not sure about by the issue of efficiency. I mean, I can choose H in any way I wish, and of course, this is going to affect the properties of my estimator. So probably I'd rather call it a GMM estimator that uses this as a moment condition with some, I mean, let's say arbitrary weighting metrics, which doesn't need to be, again, I mean, the Hessian, and it's not in that case, because again, this is, a twist that might, if you make a good choice of H, you might do a good job. If you do a bad choice of H, then you're going to perhaps corrupt the goodness that is seeded into the likelihood function. So again, I mean, I think the bottom line of this is just we are, I kind of think, again, efficiency improvement is a task, or is it feasibility, or just another way of presenting things, and which I think I'll probably buy a bit more happily. And again, if feasibility is the issue, maybe, I mean, it would be good to compare for a given model, maybe even a simpler model than the one they advocated, two different type of approach, and to see what are the incremental advantages of that proposed approach as compared with a classical method, for example. particle filter. Now, let me show you. OK, so there's a second sort of contribution. Now, so here, I mean, OK, we can debate for days, actually. So we deal with very persistent data. The data very persistent, and here's just an example of what type of data. This is not the same of the author. This is just the correlation function of the absolute value of the standard pool using about 6,000 data. So these are the type of, this is a snapshot. OK, so for example, this is the dot-com crisis. This is the new crisis. This is the 90s, the rally, and so forth. OK, so it's just a shortcut of what they did. If I face in this data, of course, the big issue is persistence. There is a lot of persistence in the data. And then we say, OK, how can we capture this? I mean, some people would say low memory could be one way. We know that low memory is a non-Markov process. But that's, as I said, you can handle this if you want in classical way, or there are other less sophisticated ways. But if you don't want to do this, you sit in the regime switching. And we know from Diebold and others, and also statisticians who work on Mikosh, we know that in alternative description, if you have a switching model where the states are very, very persistent, very persistent. But this means that, of course, if then you want to adventure into simulation-based methods, in order for your simulator to explore the distribution, it takes a long time. And so that's why I say, OK, but I mean, are we really getting an enormous amount of computational gains as respect to classical method? Perhaps, but I mean, I think this should be thought especially well, since we especially deal with this type of behavior. So that's about it. And of course, in general, we know that simulation-based methods, again, for sort of geometric ergodic processes, they work pretty well. Within root, we can handle that because there is a easy way to transform them into super sort of short memory processes. When you're in between, then things can be tricky. It's the same discussion here. So it's the very persistent states which sort of keep us working hard to explore the distribution. Test, they have this nice test, moment condition test, for which, again, they propose the particle filter. I would say that, since there is some theory going on, and they advocate that they have to advocate this particle filter because there's a problem establishing the asymptotic distribution. But remember, here we have to do it with a perfectly specified parametric model. So bootstrap could be another way that you can handle, for example. It's a classic way by which we can handle the limit covariant metrics of the statistics that we wish. And perhaps, again, which one is the best? Well, again, it depends. It's a computational issue, but I think we should, it's something that is on the menu, and perhaps it's something that some people will think of as a first choice. Rationality test, that's very interesting, but remember that rationality test is a joint test of the model of rationality. So in that case, I mean, of course, when you have, say, a rejection of the node, you have to remember, is the rationality or is the model? And again, this has to do, this arises whenever I deal with a fully specified sort of type of stuff that as the one that also are looking. But I think we should keep this in mind when we keep going and you do sort of dynamic inference in the way that they aim to do. 30 seconds. So okay, so they, for example, about application. So the model, of course, is a sort of prototype model. If you really want to understand, beliefs or theories on assertions, and this is something that, for example, I was discussing also with Peter. So if you want to forecast the future, we know that in the industry, people look at a vast amount of information. Okay? The problem there is like, I want to forecast some aspect of distribution returns, and say, for example, if I'm in the first week of the month, I know that the first Friday is a blip because the non-farm period is issued. And so as new information arises, that this is coming in, and it's going to change the distribution of the data. The problem here, of course, is this data very often is of mixed frequency. And again, the Kalman field can handle this very elegantly. And if you want to go on, then you might want to think about this issue also for your simulation-based methods. A couple more comments. This is not with the paper. For example, I found funny that on the result, you remember there was this kappa bar, which was the number of states of the multifractal, and as kappa was increasing, then basically the model was moving from the high frequency to the low frequency, and I found this a bit strange. So I just, I have to see why, because it's like, say, I want to describe a time series model, and I start from the noise, and then I move into the trend, which probably, there are good reasons, but maybe you could explain this for the one who are not more familiar. And also, for example, and more stuff is about the forecasting, which is very interesting. But is this real-time forecasting? Is it the forecast that people do today to forecast tomorrow? Or or not, because this makes a whole difference. Whether this if you want to sell this approach and this estimation strategy, then the people want to reuse information in an operational way. And again, probably it is, but some clarification perhaps would be needed. So thank you very much. It was a terrific thought, and I look forward to see the sequel of this paper. And now I have to get the flowers.
Thank you, Paolo, for this nice discussion. First of all, I would like to mention that the learning model that we use is not ours. It has been introduced by Laurent Calvé and Adlai Fischer in 2007. So, it's written in the abstract. I realized that I did not mention it on my slides. I'm sorry about that. So, in this learning model, we have a nonlinear model, right? We have isoelastic utility function, so we cannot apply a Kalman filter. So Kalman filter is out; it's not a possibility. That's why we use this indirect inference approach. You mentioned the GMM approach. So GMM is not feasible here because moments we cannot compute analytically the moments. And that's why we use indirect inference. Now, GMM, of course, can be considered as a... So GMM is an indirect inference estimator, but not vice versa. And the one that we use is not a GMM. You mentioned the efficiency gain. You asked the question about the efficiency gain. So the efficiency gain comes from the fact that we use, in the indirect inference estimator, an auxiliary parameter that is very close to the structural parameter. We use the full information maximum likelihood estimator, and the full information is very good. It's already in the neighborhood of the learning model. It's actually nested in the learning model. The only sample moment that we use is it's sometimes we use the sample return median. Now we did for the efficiency, the variance of the indirect inference estimator is proportional. I think is proportional to the variance of the auxiliary estimator, and it's inversely proportional to the derivative of the binding function. What is the binding function? Is the probability limit of the auxiliary estimator. And it means that we need to choose auxiliary parameters that exhibit the biggest, the highest derivatives with respect to the structural parameters. And this is what we do in our we consider a variety of statistics, and we study the binding function, and we really choose the one that exhibits this property, the biggest derivative, largest derivative. And for the variance, we choose the one that provides the smallest variance for the auxiliary estimator, and since the indirect inference estimate is proportional to that one, is the best choice. We show also, by the way, the efficiency gain on the box plots that I showed you. Now, just two last comments. So the dynamic test, you mentioned it's a joint test. Of course, it's a joint test because it implies it's a test about the hidden state, and the hidden state is specific to the model. So indeed, it is a joint test. And for the forecast, it is out of sample, it's real time. Okay, thank you.
Please visit us at www.agc.edu.